Also do a quick mic check. If you guys can hear me, that would be great. Um, okay, so let me quick. Oh, seems like it got set at the very end. Okay, so um, my name is Sam Mergendahl, and I'm a third-year PhD student here at the University of Oregon. I work closely under the direction of my advisor, Dr. June Lee, who is also the director of the Center for Security and Privacy, which I also work at. And today I'm going to be talking about, like she mentioned, the source end distributed denial of service defense system that our lab has been working on for the last year or so. And this system is designed for Internet of Things networks and particularly designed to defend against IoT-enabled distributed denial of service attacks. So essentially today what I'm going to be talking about is sort of just introducing the Internet of Things and source-end distributed denial of service defense systems and some of the difficulties that these defense systems may have. And then I'll go into talking about our forward system, which is designed specially to defend against and fix some of these struggles that traditional source-end defenses have. So I'm sure that many of you now in 2018 have heard about the Internet of Things and IoT and its expansive growth, but we can see that it's still growing immensely in terms of spending on the Internet for the Internet of Things and different areas of IoT growth we're seeing an explosion of, and not only spending, but we see the market share is increasing, especially in the industrial IoT and you can look at surveys across many of these different environments, and we see that many of them label IoT as a very important next thing that they want to focus on. But the problem is that a lot of these IoT devices, when they are deployed, remain unprotected and can often become targets of these botnets that can grow really fast. So for example, there was this famous botnet from 2016 called Mirai that leveraged a lot of smart home devices such as security cameras or routers. But now we're seeing, 2017 comes along and the Mirai botnet sort of expands and becomes what is they're calling the Reaper IoT botnet, and it's also infecting a crazy number of devices. And further now in 2018, we're seeing another IoT botnet called Satori that's expanding. So these IoT botnets themselves are a concern, but they also have the secondary threat of being able to launch immersive, large-scale distributed denial of service attacks. So the famous one, of course, is the Mirai botnet launched the attack against DIN in 2016, which was able to achieve up to a terabit of DDoS traffic. And then, but at the same time, we're seeing these other IoT botnets also participating in these distributed denial of service attacks. So Reaper in 2018, and also this year, we're seeing Satori is attacking Ethereum mining rigs with distributed denial of service. So really, we can attribute this increase in DDoS attacks to these IoT networks. We're seeing almost a doubling of the number of DDoS attacks from 2016 to 2017. And it's pretty clear that a lot of this comes from these immersive IoT botnets because criminals can now take advantage of them and take down a company for less than $100 in sort of these borrowing of the IoT botnets to launch their attacks. So one one promising defense against these IoT-enabled DDoS attacks is a source-end DDoS defense system. And a system like this detects and thwarts the attack traffic before it ever leaves the original network. So this can be useful because it's a lot easier to handle these giant DDoS attacks close to the attack sources before they propagate out of control or before you run into problems with IP spoofing and things like that. So these source-end defenses can also play a pivotal role if they want to participate in some of the collaborative DDoS defenses that are quite popular now in the last year or so, because they can sort of remove liability from their network, and their collaborator, when they're under attack, can guarantee that this network running the source-end DDoS defense is not participating in the attack, or it can sort of initiate its defense more specifically. So these source-end DDoS defenses operate in three main phases. First, they have to detect the attack. So like I said, they could receive an attack notification from a collaborator, or they can self-sufficiently by looking at traffic statistics or things like that. And then once they realize that there's an attack going, they can run traffic classification to sort of label each of the devices in its network to see who is participating in the attack and who is simply a benign user. And then the last stage of these source-end defenses is you have to respond to these classifications that you've given. So typically you'll simply filter the bad connections and allow safe passage for the good. But the problem arises in IoT networks because false positives are going to be significantly detrimental in these types of environments. And what I mean by false positive here is this source-end DDoS defense system misidentifying a benign connection as a malicious connection. So then if they move on to the response phase and they filter this misidentified connection, it's going to drop this IoT devices traffic, which is going to lead to unnecessary retransmission, a reduction of good put, and eventually an excessive energy consumption, which for many IoT devices is going to lead to loss of its precious battery life. But at the same time, these source-end defenses must still maintain a close to zero false negatives, which is the whole point of the defense, is that they want to make sure they're not misidentifying malicious connections as benign, because if they then allow safe passage, they're going to fail to properly mitigate the attack coming from their network. So under these constraints, it becomes very difficult to categorically label traffic in these IoT networks, because a traditional source-end defense system might be able to sort of keep their false negative rate relatively low and sacrifice it by having a little higher of a false positive rate. But that's not possible in these IoT networks. So, and it's because these source-end DDoS defense systems are going to inevitably encounter traffic that it's going to label with low confidence. And so for the rest of the talk, this traffic that is being labeled by the classification as with low confidence, we're going to call suspicious. And the crux of the problem really becomes if the defense filters the suspicious traffic like a traditional source-end system will, then it's going to inevitably filter some of the good traffic, which leads to these unwanted negative effects on benign traffic in IoT networks. And if they allow safe passage of the suspicious traffic, it inevitably will fail to comprehensively mitigate an attack. So what we really need is this a new idea of a more efficient and effective response to this suspicious traffic. You can't just go through the simple filter or don't filter like we used to in the past. Which leads us to the forward system, which stands for fast retransmit as a weary but ample response to the distributed denial of service attacks. And so I'll go through some of the components of forward in this next section of the talk, talking about the different ways of labeling and our efficient two-fold response. So we wanted to design forward so that it's placed at a gateway of a generic IoT environment. And what I mean by generic here is that the IoT network, really the only assumption we have is that it's maintaining this wireless connectivity between low power energy constrained devices. We really could have the IoT network be, maybe a smart home of devices connected with light bulbs, or sensors at a nuclear reactor aggregating their traffic together, or a smart city. The point is, we really want to just have this be a defense system that we can place in any of these IoT environments without leveraging some specific component of the IoT environment itself. So at the end of the day, it comes down to two main goals that Forward has. It wants to throttle all malicious traffic that attempts to leave the police network, and it wants to make sure that during this process, it's not actually throttling any benign traffic that's trying to leave the network. So for example, let's say we have this situation where there's some malicious nodes that are employed in a botnet that are sending red malicious traffic, but there are also at the same time good nodes within your network trying to contact the victim server and sending green benign traffic. And the overall goal is that we want to make sure Forward throttles away the bad traffic before it leaves the gateway and still allows safe passage of all of the good traffic. So we really designed this Forward system based on these fundamental characteristics of an IoT environment. And what I mean by that is that we're going to follow two principles. First, we want to adopt this conservative approach to avoid dropping benign traffic like I've been mentioning. And we do that by we're not dropping any traffic that we cannot definitively discern as malevolent traffic. And instead, we create this sort of twofold response system that I'm going to be talking about, which devises a signaling mechanism to handle these suspicious connections. And second, we want to make sure this defense doesn't rely on any installation of new hardware or software on these IoT devices. Many IoT networks are almost physically unreachable or possibly incredibly lightweight to the point where they can't even run these new installation of hardware or software. So our design follows this basic flow of a source end DDoS defense design, right? We have an attack detection, which can become through anomaly-based detection or victim end collaboration, whatever it might be, which flows into the labeling procedure or classification. And then we really get into the main contribution of Forward, which is this two-phase response to this specific connection labels that it receives. But at the same time, we've designed this flexible architecture so that in the future, anybody who might be using Forward can easily swap out different attack detections or classification procedures that it might like to use. So I just want to briefly talk about the labeling procedure that we're going to be using throughout the rest of this talk, even though it's not the main focus of our system or any of our main contributions, because these connection labels really act as an input to the Forward system. So what we're going to be doing is using the observation component of the previous source end DDoS defense popular defense solution called DWARD in order to closely identify how our response is improving previous responses. But at the end of the day, you really want to stress that you can swap out this component for different machine learning algorithms or victim end collaboration. The key point is that even with powerful machine learning algorithms, they're still going to encounter traffic that they have to label with low confidence. So the DWARD's monitoring is really at two levels of granularity. First, it does the attack detection by looking at the aggregate traffic in your network and to each particular destination. So for the rest of the talk, we'll be calling this an ag flow, and I just want to. This is all of your network's traffic statistics going to this specific destination. And when something weird at the aggregate level is going on, then we can go in and sort of at a more granular level look at each node in our network and see and try to discern which one of them is participating in causing this to happen. And so we label them good, bad, or suspicious of each of these connections. And now, once we have these connections, we need to start our response to them, right? So good and bad connections are relatively easy to respond to. We can throttle the bad connections, but allow safe passage for the good connections. But forward must also be able to respond to the suspicious connections. So what we do is we employ the fast retransmit mechanism of TCP congestion control to reduce their sending rate. And what I mean by that is that we send 3 duplicate acknowledgments of a previously sent segment to the suspicious connection, because if it is following congestion control, in accordance to multiplicative decrease in fast retransmit, the sender will cut its window size in half and then immediately retransmit this segment that it thinks is lost. And so what we do is we call this set of duplicate acknowledgments that we're sending to the sender a signal. So in order to make this a little more clear, I just want to run through a quick example of if the device is running TCP Reno, for example, how the forward system works. So in the past, there will have been some acknowledgement that the receiver sends back to the sender. And so at the time of the attack detection, forward will have logged that acknowledgement and it can send it to the sender again, which is going to cause the sender to retransmit the segment that it thinks is lost, or in this case, the data 9 segment. And then once the traffic returns from the previous sending of the round trip time, it'll be back on track with sending and increasing its sending window by 1 each round trip time in accordance with TCP and congestion avoidance. So this process, we can see, really has 4 main benefits. So one, the first thing is that our signal is able to identify compliance with congestion control. So forward can relabel the non-compliant connections as bad within 1 round trip time and begin to throttle them if they don't follow congestion control. And second, we see that the sender is decreasing its transmission rate. So remember, at the end of the day, we don't know if the sender is good or bad. So while we're testing for congestion compliance, we want to sort of decrease its transmission rate in order to mitigate the attack if it is one. So passively checking the compliance might not be fast enough. Third, we see that, so in the past, some systems have come out with, we can throttle the traffic to test for congestion control compliance, and this achieves the same 2 benefits that we just mentioned, but our signaling mechanism will achieve the same benefits, but in a way that has significantly less retransmission, doesn't cause things like timeouts and things like that, so that throttling and dropping the traffic might do. So reduces retransmission, which increases good put and eventually energy consumption. And now I want to show that we can extend this easily across TCP variants, because each of these different underlying congestion control algorithms will still respond to the signal in a way that achieves the benefits that we're mentioning. So I know that this is a really complex, these flows of TCPs have been well looked at in the literature and things like that, but I just want to sort of point out that we're able to maintain the same benefits across these different variants. So we have identifying compliance with congestion control. We see that they're reducing their window and reducing their transmission rate in case they're a part of the attack. And then we also see that the retransmission and timeouts and things like that are maintained relatively low. So now the second phase of our response system is going to be defending against sort of what we call smart attackers. So an attacker might design an attack specifically to evade our system forward. And we want to make sure, in order to prevent that, we have to define sort of an allowed transmission rate for each of these suspicious connections. Because we can relabel ones that don't follow congestion control as bad, because now we know for sure that they're malicious, but we cannot relabel the ones that do follow congestion control as good, because they could be one of these smart attackers. So we enforce this transmission rate until the attack egg flow is relabeled as a normal situation. So what we do is we also look to TCP and employ the flow control mechanism of TCP. And what I mean by this is, in TCP, a receiver provides a flow control service in the form of a receive window, which informs the sender the amount of available space in the receiver's buffer. And you can see that this provides a precise definition of what we want for an allowed transmission rate, because we know that they're following congestion control, so there can sort of limit the possibility of a link along the path failing and constituting a DDoS attack. And now we can also limit the possibility of a DDoS attack occurring at the source itself. So we can leverage this sort of hint from the receiver of what they want them to send. But the problem is if we're just constantly monitoring these two definitions of a allowed transmission rate, this is a very expensive process and requires state maintenance. So our whole system is designed so that this only has to occur when it's absolutely necessary, and it really limits the amount of state maintenance that we have to have. So I just want to quickly review everything that I've talked about so far. We see attack detection can occur through victim and collaboration, or it can self-sufficiently detect an attack at the gateway of the network. And then once it does that, it goes through and it labels each of the connections in its network as good, bad, or suspicious. And it is going to allow the good traffic to go through, throttle the bad traffic, and then for the traffic that we can't discern as good or bad necessarily yet, we're going to send them a signal and initially allow their sort of reduced transmission to go through for the time being. And then if they fail to comply with congestion control, we relabel them as bad. And for those traffics that do comply to congestion control, we have to set up this allowed transmission rate and throttle them whenever they attempt to send more than receive window. So now one main thing that you might ask is that forward is based and it's deriving its ideas from these aspects of TCP. So we want to show that forward is actually able to extend to other types of connections. And so I just want to mention, traditionally, application will be using UDP if unreliable communication is sufficient. So you might have some application where there's an IoT device that's probing its location to some server and periodically sending the information. And even if some of this information is lost, the server can still infer what the application actually needs based on previous and future information. So, and the key point here is that under these types of applications, there is no need for an efficient response because there is no reliable communication. There's not going to be any retransmission if packets are lost. So we can simply throttle the connection and take that suspicious traffic and treat it as if it's bad for the time being. But it sort of extends beyond that because in the last couple of years, there's been some interesting work in IoT where these applications desire the reliability of TCP, but they're going to do it on top of UDP. So for example, this CoAP application. And so these connections will retransmit their lost packets similar to a TCP connection. And so forward can't simply throttle, and we do need this efficient response still. But the key point is that these connections require reliable transportation. And this is going to be using some sort of acknowledgement. And there's some study in the literature showing that if it's going to use this acknowledgement, then a congestion control will improve their sort of connections efficiency, which IoT desperately needs. So, for example, I just want to show that forward can create its signaling mechanism based on this acknowledgement. It doesn't need to be TCP. It's really creating the signaling mechanism based on the acknowledgement. So I just want to show an example of this. And so I mentioned the CoAP protocol. In the last year or two, there's been some really interesting research on how to add congestion control onto this. And this summer of 2018 was the most recent paper was published, PCOCA, which I believe stands for Precise Congestion Control for CoAP. And so I just want to show the same flow of it. It's possible to extend forward to this. And this congestion control algorithm isn't necessarily window-based like TCP, but so instead what it does is it uses this retransmit timeout to sort of decrease the sending rate of the stream of packets. So you can see that if data 9 is lost along the way, it waits the retransmit time and then retransmits 9.2, which is the same packet but just with a sequence number on it. And then so what happens now is later if there's an attack detection, forward can retransmit that same acknowledgement to the sender which is going to then calculate the round trip time since it sent that first packet, which is going to increase its retransmit timeout, which then will slow it down in the future when there's another packet that's lost. So it's essentially the same thing where our signaling mechanism is reducing the speed at which this CoAP sender is sending. And we can check for compliance of this and things like that. So now I want to sort of conclude my talk by looking at some evaluation of how and what the extent is of these signaling mechanisms and our efficient response. How much does it reduce negative effects on benign traffic, and are we still able to stop malicious traffic and mitigate the attack? So what we do is, like I mentioned before, we're going to compare forward against previous source-end DDoS defense systems, the previous one, DWARD. And because we've set up our flexible architecture, we can use DWARD's labeling and detection component in order to properly evaluate the response system. And what we do is we simulate sort of these mathematical models of the two systems that we've created and see their effect on retransmission, goodput, and energy consumption. And then what we do is we extend this and we use real-time experiments to estimate the forward's ability to mitigate DDoS attacks. And we show that the two-phase defense is actually able to mitigate more attacks than DWARD is, our previous ones that just look at throttling and for congestion control. So first we see that there's a reduction in retransmission between the two systems. So those three TCP variants that I mentioned earlier, Reno, New Reno, and Westwood, we simulate over the two systems, and we sort of see this trend as the window size increases at the time of attack detection, DWARD is going to drop more packets initially. But forward is never dropping suspicious traffic, so it's going to be causing close to zero. In fact, if you look along the x-axis, you almost can't even see the forward lines because they're so close and essentially zero. And in fact, you can see across all of these TCP variants, we're still reducing retransmission regardless of which one we're under. Some of them you have a larger reduction and some of them have a smaller one, but it's still, regardless of whatever the TCP connection is, we see a reduction. And in fact, if you average out these graphs, we see it's reducing retransmissions by a factor of 200. So similarly, we see as the window size at the time of attack is increasing, the good put is also able to increase because it's sending more traffic, but DWARD's good put is less than forwards. And this is for the same reason that it's going to be dropping packets, which is going to cause the transmission to be muddled with retransmissions and timeouts and things like that, so that the IoT device is actually able to transfer its traffic quicker under these two systems, under forward. So the consequence of all of this is the main selling point is that we're going to be reducing energy consumption under using forward instead of using DWARD. If the two systems are in place, we again see that regardless of the TCP variant, we're going to be reducing energy consumption on these benign IoT devices based on our two-phase response. And so we also want to look at if we modify some of the parameters in DWARD, what effect does this have? Because maybe we can set it up in a situation where this isn't going to be the case. So what we're looking at here in this graph is TCP New Reno, which is if you look back at the old graphs, we see that it's the TCP congestion control with the least improvement. So we just want to show that even in that situation, monitoring DWARD's parameters still gives us an improvement. And so the parameter that we're looking at is FDEC, which is sort of represents the rigor of the DWARD system. How strictly does it want to respond to an attack that it thinks is occurring? And we see that as it becomes stricter, or FDEC decreases to 0.1, then we see an increase in the improvement that forward has in both retransmissions and exponential increase in the improvement for good put. So now we want to sort of switch over and show that forward is also able to just as effectively, if not better, respond to malicious traffic than dward. So first we set up a sort of naive attacker that's just going to flood and do a TCP SYN flood attack. And we see that because the two systems have the same attack detection, they notice the attack at the same time and begin to respond at the same time, and both successfully throttle the traffic down to almost nothing, to the min rate in the parameter setting. And you see that the graphs almost look identical, but remember I mentioned forward allows this sort of negligible instant of extra DDoS to go through that you can't even really notice because it's able to relabel a suspicious connection as bad if it fails to comply with TCP within one round trip time. So it essentially responds in the same manner as dward. But when we start talking about a smarter attacker that we designed to sort of follow congestion control and see if we can still attempt to flood the receiver with TCP SYN segments, we see that under dward, the attacker follows congestion control but not flow control. So it's able to still send traffic at more than what the receiver can handle. I know it's a little hard to see on this, but there's a dotted line going across, which is the receive window that we have static throughout the experiment. And our attacker that we designed is able to still overwhelm the server in this sort of periodic manner. And we ended the experiment at 30 seconds, but this sort of will repeat and potentially could still cause an attack. Whereas under forward, we have this two-phase response, so the smart attacker is never able to transmit at a pace that is going to overwhelm the receiver. So really, at the end of the day, we don't know whether this device is inherently malicious or is inherently benign. So what we want to do is we want to allow the traffic to be sent from this device in a manner that isn't going to negatively affect it, but is also going to be able to prevent any sort of attack. So you can see that this traffic flow is following congestion control and is following flow control. So it really limits the ability for this device to participate in an attack. So that's sort of all I have for the talk today, and I just would like to take a second to thank the co-authors of this work that we've been working on for the last year. And if you want to look into more details after the questions, I would be happy to point you to a publication that we had this summer. Thank you for listening. Is there any questions?
As a reminder, if you have questions for Sam, please put them in the chat box. All right, well, there doesn't appear to be any questions at this time. So thank you very much for your presentation, Sam. We're going to take a quick break, and at 2 o'clock, we'll have Dr. Payne.